Good afternoon, everyone. We'll just wait a quick second until we're past noon that everyone can join. Then we'll get started. We'll wait another couple minutes. I'm sure lots of people are just tuning in. Okay, so that we stay on schedule, I'll get us started. Welcome everyone to the next installment of the Tunnel Association of Canada Young Members Tunneling 101 webinar series, this time in support and conjunction with the Underground Construction Association Young Members. We're very happy to be encouraging this Canada-US international collaboration on the increased sharing of knowledge between both organizations and also young tunnelers and the tunneling societies and community at large within the both countries. Today we have Mr. Martino Scialpi, who is joining us today for his presentation. Mr. Scialpi graduated from the Polytechnic University of Turin in Italy in 2006 as a civil engineer and environmental engineer with a Master's of Science in Tunnel Design and Construction. Since then, Martino has been particularly active in mechanized tunneling as well as TBM design, operation, and modification for difficult ground conditions. His experience as tunnel manager for contractors, project manager for a TBM manufacturer, and tunnel designer for engineering firms span 5 continents. In 2020, Martino joined the program management organization of DC Clean Rivers as tunnel design lead and is currently performing construction oversight for the Potomac River Tunnel project in Washington, DC. Based in the US for the last 15 years, he's the technical director of ARX USA since 2022. Over the years, Martino has contributed to WTC, RETC, NAT, and TAC publications concerning mechanized tunneling in challenging ground conditions and machine performances. He is a member of the UCA of the SME Executive Committee, chairing the UCA Mentorship Program, as Vice Animateur for the ITA Working Group number 14, Mechanized Tunneling. Martino is leading task group number 2, recommended guidelines for TBM specifications. We're looking forward to seeing these guidelines published at the next World Tunnel Congress in Montreal coming this spring. Mr. Scialpi, thank you very much for your time. Thank you very much for joining us. And with that, I'd like to pass the mic over to you and hear your presentation, please.
Thank you, Graham, for the detailed introduction. Yes, we're working to get those guidelines released by the next conference in Canada. But today we're going to be talking about something somewhat related to TBM specifications. It ties into it a lot. Today's presentation is about multi-criteria analysis for TBM selection, particularly for complex jobs, as we'll see in the rest of the presentation. And this is a bit of a continuation or a part 2 of the presentation that was held on December 10 by Stefan Ferber on innovations in TBM technology. So let's get to it by spending a few seconds on the outline. We'll make a quick recap on the types of TBMs and their range of application. As I said, most of what we know about it has been already covered by Stefan earlier in December. We'll talk about when a TBM selection analysis is actually recommended. We'll start reviewing the GBR and GDR analysis process, which is the starting point of any TBM selection analysis, the ground behavior and geohazards identification as a consequence, identification of other factors or other performance fields above and beyond geological and geotechnical. And then we'll get to see some of those multi-criteria comparative analysis from the most qualitative ones into semi-quantitative and quantitative. We'll have a few examples of each one of those. Conclusions at the end of this presentation. So here we start with the types of TBMs. As I said, this has already been extensively covered in December. I just wanted to show you one more time that typically we classify them as hard rock and soft soil. The hard rock machines are generally three different types: gripper or main beam TBMs, single shield and double shield. In soft soil, we are very used to define or recognize EPB and slurry machines, but we also have machines that are able to adapt to mixed mixed phase and changing ground conditions that are the so-called hybrid or dual mode or multi-mode type of TBMs that have been particularly developed in the last 20 years. Range of application of hard rock machines. Briefly through these, when to use a gripper or main beam TBM, it's typically good rock quality with self-supporting capacity ground, where extremely poor or faulted ground is not expected, and where high water inflows are also not expected. As you can see on the right side here, there is a typical layout of a gripper or main beam TBM. In the same way, a single shield TBM would adapt instead to fair, poor quality rock mass, still self-supporting. Extremely poor faulted ground can be expected. Water inflows are also can also be anticipated. And in this specific case, as well as the double shield we'll see next, the single shield is able to protect workers from falling rock until the concrete segmental lining is installed right behind. Double shield TBM, a lot in common with a single shield. The main differentiator here is the fact that the double shield is able to advance and install segmental lining at the same time. It would adapt to poor quality rock mass with limited self-supporting capacity. Again, fault zones can be expected. High water inflows can be expected. And in the same way, as I mentioned for the single shield, the tail shield there and the whole shielded section of the machine offers protection to the workers. Shifting to the soft ground hybrid TBMs, we do know that EPB TBMs are specifically perform better in cohesive ground with low permeability, and that the use or the addition of additives can extend that range of application also to sandy and gravel soils. The slurry TBM is more suited for permeable granular soils. Polymers can be used to excavate ground containing high amount of silt and clay, can handle cobbles, lump of rock to a size that can make it through the hydraulic mucking system. When combined with these cutters, this machine is able to perform and to excavate also rock, while the hydraulic mucking system helps manage high water inflows. And then there is the whole range of hybrid multi-mode machines that obviously can be adapted to all these conditions, from soil to mixed phase to hard rock, above and under water table. With that being covered as a refresher, let's get into the TBM selection analysis when the TBM selection analysis is actually recommended to be performed. So assuming, first of all, that the TBM tunneling specification allow a choice and they're not so prescriptive or restrictive to basically indicate a specific type of machine, the assessment and the comparison of alternative approaches becomes necessary in our opinion every time either geological complexity or uncertainty define the project. So every time there are variable conditions along the same alignment, like rock, mixed phase, soft ground, above and below the water table, high water pressure, high water inflow, Well, those are the conditions that make the alignment and the project complex enough to pause and take the time it takes, to spend the effort it takes to verify which is the machine and the machine features that would better comply or fulfill all the requirements. Low ground cover and proximity to existing structures as foundations or underground utilities obviously is a discriminator above and underground, and a limited or not fully representative geotechnical investigation. It happens that sometimes we have to deal with projects that have that don't provide, for which full characterization is not provided. There are gaps of information, and that is where a TBM that can adapt itself to a wider range of conditions may be useful. On the right side of the screen here, you see a picture for a project currently in construction. This is part of the alignment of the Potomac River Tunnel north side. And I believe that in many ways, these conditions are checking a lot of the boxes we've just presented at point one. We are in a curve. We are crossing, or we will be crossing, a section of mixed phase where the rock will interface also with a paleo channel, which will be including granular material, cobbles, and boulders. We are in a very urbanized section of the alignment with a relatively low cover and a very small degree of separation with existing structure like the two tunnels you can see in the green circle here that are the metro tunnels from Vamada. So all these situations, all these conditions combined, obviously are the specific or the typical case in which more effort needs to be spent to determine what's the best machine to deal with it. In combination with physical constraints, we may be dealing with inability to change alignment, limited or no ability to perform ground improvement from the surface, limited extent of the mining site, which sometimes doesn't allow installation, for instance, of a slurry treatment plant, forcing the selection into a different type of machine other than the slurry. So logistic restrictions, as well as single access tunnel, where you don't have intermediate windows, adits, or shafts from where you would be able to launch a different type of machine. So the basic approach has always been, for a long time, been that in case where the tunnel is very long or is under complex geological condition, the tunnel method is selected based on the condition that is prevailing along the alignment. But we are trying to move forward past that approach, and we are trying here to leverage the evolution of TBM technology over the last 20 years. Understanding project requirements and constraints, assessing the risk that is associated to each one of those anticipated conditions, and selecting the TBM technology that meets requirements and provide best possible mitigation measures in all conditions, not just the condition that is prevailing along the alignment. The current TBM technology allows us to adopt this better approach. Here is the process we are going to review together in the next slides. It's a risk-based process that takes us all the way down to selecting the most appropriate type of TBM. It starts with a review, in-depth review of the GBR and GDR, identification of ground behaviors and geohazards, putting together a georisk matrix, as you would do every time you're dealing with risk assessment, typical risk assessment, identification and mitigation of mitigation actions by each TBM type, as well as scoring each TBM type based on residual risk. In parallel with this, you would need to study project specifications and drawings, understand contractors' means and methods. Most of the times, this effort of performing an analysis for TBM selection is provided to contractors. So it is of fundamental importance to understand also what their preferred means and methods are. Identify other TBM performance fields that may be affecting the decision, and score each TBM type accordingly. At that point, we combine the results obtained by these two parallel paths into a matrix, and that allows us to select or make a recommendation on the best TBM type for the project. So let's get to it by starting with the GBR and GDR review and what that means in terms of TBM selection. First of all, for those of us who may be not super familiar with a geotechnical baseline report and a geotechnical data report, the first one is a contract document that establishes best possible understanding or interpretation of the subsurface conditions. And the main purpose of that document is to clearly define and allocate between the two contracting parties, the contractor and the owner, the risk associated with the ground conditions and the behaviors that are being baselined. The geotechnical data report is also a contract document that is developed by the designer's geologic and geotechnical engineer, which is presenting or collecting all the factual information gathered during the geotechnical investigation program, which includes logs, photos, field, and lab test results. Obviously, the intent and the purpose here is to have a baseline statements in the GBR that are consistent with the data gathered in the GDR. And for your reference, these definitions and a lot more can be found in the geotechnical baseline reports guidelines, which is a guideline published by ASE and UCA of SME, but I believe is widely adopted anywhere in North America. And if you want to learn even more about this, I recommend attending the webinar of February 19 by Danny Delaloy on best practices for GBR and GDR on underground projects. That would be a great a great opportunity to learn more about these two documents. So in the GBR for rock TBM tunnel, rock characterization is typically based on characterizing rock type, geologic formation, mineralogy, intact rock properties like the bulk unit weight, the compressive strength, elastic modulus, Brazilian tensile strength, and the abrasivity index. Degree of weathering, degree of fracturing in terms of RQD, joint orientation and characteristics are typically included. Rock mass classification, not always included, but very useful to have. GSI and RMR, we'll talk about a bit more about those later. Groundwater, depth, conductivity, hydrostatic pressure, location of confined water, the chemistry of the water itself, as well as the predicted water inflow, which is not always included. And then contamination, of course, of the ground and the groundwater, as well as the presence of gas. For soft ground tunnels, the soil characterization is typically based on soil type, thickness of the strata, blow count, grain size, percentage of fines, abrasivity of the soft ground or the matrix, selected ground classification system that describe behavior. We'll take a quick look at that later. Clogging potential is extremely important, and it is a decisive factor when it comes to TBM selection on many projects. Obstructions, natural and man-made. I'm referring to existing utilities if man-made, or foundation piles that are abandoned in the ground, as well as cobbles and boulders if they are natural. Groundwater, depth, permeability, hydrostatic pressure, this is a lot in common with rock, chemistry and water inflow, and again, contamination and presence of gas. The independent GBR and GDR review and interpretation then happens by reviewing the raw data that is generated during the geotechnical investigation and that is included in the GDR. It gets into characterizing the ground conditions independently with specific focus on data from the tunneling zone, which is the tunnel horizon, the tunnel envelope, plus minus 1 diameter, And you'd be surprised by how different that interpretation may end up being versus the one provided in the GBR that is typically including all the data at any depth. Comparing results to charts or ranges including the GBR, identifying or trying to resolve any inconsistency between the independent ground or characterization we perform as consultants and the GBR, and then defining the likely behavior of the anticipated ground with means and methods in mind. Typically, the GBR is providing an indication. There is a paragraph specifically dedicated to ground behavior or interaction of the ground with the excavation methodology, but that doesn't always cover all the details contractors need. And then determining the geohazards and related potential impacts on the progress of the work during the tunnel excavation, being that the real input we need to determine what's the best machine for the job. You may be wondering, what's that picture on the right side? Well, that is a picture I wanted to include as a job I was on many years ago. It was my first job, actually, where obviously we entered with our double shield TBM into a very highly squeezing ground conditions to the point where what you see there is the tail shield completely bent and deformed by the convergence of the ground around the machine and the displacement, the severe damage to the lining, as probably the best example I can make right now of conditions that were not predicted, mostly because of a lack of information over an extremely long and deep tunnel, which didn't recognize these as a risk. Here are some of the examples of results of our the independent analysis review of the GBR and GDR we as ARCs perform for contractors. As you can see, there are differences, and these are just a few of the things I can show you, but when the rock type for that specific job, when you consider the tunnel envelope ±1 diameter, which is the area around the TBM that really counts to make some of the decisions functional to the TBM selection. As you can see, there are differences, as well as in the UCS. The distribution of the UCS isn't necessarily the one the GBR is baselining, because we are considering most of the times a different range of data, the one that in our opinion is more relevant. The grain size distribution, in this specific case, we consider all the data, but as you can see, our replotting of the grain size curves isn't necessarily matching the boundaries set as baselines by the GBR, and that is very interesting to know and to have as an information, as well as the clogging. On this chart, you can see that the medium and high clogging baseline is probably on the conservative side when you consider only tests from the tunnel envelope and the area of interest, or the area of interest of the tunnel. Here is another example of a geomechanical characterization we perform for rock tunnels. Every time the GBR doesn't provide all the informations that are actually needed, in our opinion, to characterize the ground and the behavior of the ground versus the type of machine needed for the job. So in this GBR, we only have RQD, UCS, and BTS provided and baselined. And on the basis of the geostructural and intact rock properties, the mechanical quality of the rock mass was estimated by us, determining the GSI and the RMR with a probabilistic approach. Obviously, the RQD was not sufficient to describe the rock mass conditions and classify the behavior, so we had to do something more. And with the data available in the GDR, we managed to determine GSI and RMR. This classification or the determination of these parameters helps define homogeneous zones along the alignment or ridges that are not just based on parameters distribution, but also on the actual quality of the rock and predicted behavior. So here is an example of a resulting profile with the geocharacterization of a tunnel in rock. As you can see, the alignment with the geoprofile provided in the GBR. The part below, the section below, is the part that we developed independently. Zooming in, this shows obviously formation, soil and rock type at the tunnel face, and anything you may need for geological characterization, for a better geological characterization. But the most interesting part is no doubt the geotechnical characterization of it, where we, as I said, provided not only a table, but also a distribution of RQD and GSI and RMR along the alignment, which is much more granular and better information to have for contractors when they're estimating the job. In the same way, the hydrogeological characterization is developed and provided here along the alignment in terms of hydraulic conductivity. Another example of this is this tunnel in rock, for which again, we ran our own independent analysis. We provided geomechanical characterization with RQD, foliation joint orientation, Q value, RMR, and GSI. This is because, again, more indexes, the more the better. In this case, this isn't a tunnel that is only partially excavated by TBM. There are also sections, drill and blast. So having those parameters is definitely beneficial. The hydrogeological characterization is part of what we plotted along the alignment, as you've seen also in the previous example. But this time we went beyond that by also calculating in a tunnel where water inflow, a lot of water is predicted. We also calculated what amount and where. Another example of a tunnel slightly different. This isn't entirely rock, but rock and soil. The characterization here obviously had to tie into parameters, soil parameters, as well as rock parameters. And we did the best we could also to characterize the mixed phase conditions at the transition between rock and soft ground. And here is the last one, soil and rock again. As you can see, this is an extremely heterogeneous alignment characterized by granular material as well as silt and clay. So in this case, particularly in this case, was very beneficial to develop this profile with a specific characterization, identification of sub-reaches within the reaches that were already included in the GBR in order to provide, again, the contractor with a more granular interpretation of the expected ground conditions and behavior along the alignment. So this is the data that you would typically need to then determine geohazards and ground behavior as a function of geohazards based on ground behavior. So the next step in the process, in that flow chart we saw at the beginning, is the determination of the excavation behavior and related geohazards. One methodology we like to use takes advantage of the multiple graph developed by Russo, which is an ARCS employee. But again, this is more for your reference. You find plenty of literature on this specific methodology developed by a colleague of us. And the implementation of the multiple graph approach is based on probabilistic analysis of variability of GSI and RMR. So you understand why it's so important for us to determine those two parameters and the combination of those two with the overburden conditions. So you see this is a multiple graph, and by basically working your way through the 4 charts, it's then possible to determine the probabilistic occurrence of geomechanical hazards in each tunnel reach. So you would repeat this effort for each one of the reaches along the tunnel alignment. When it comes to soft ground, there are engineering properties that are determined to basically characterize soil behavior. They are listed here: strength, compressibility and consolidation, permeability, density and compaction, as well as plasticity. All the above can be determined as a function of grain size distribution and Atterberg limits, which are typically included in the GDR. Without getting into too many details, a typical reference for the industry is the Tunnelman's classification for soft ground behavior developed by Terzaghi and Hoyer. So the most typical geohazards, let's get to the core of it. The most typical geohazards in rock are listed here. In our experience, those are the ones that we more often identify on tunnel projects. And these are the ones that then become input for determination of risk and TBM selection. Unstable wedges, caving, rock burst, low rock cover and crown instability, squeezing and shield jamming with long and deep tunnels, high abrasivity and color wear, extremely hard rock to borability limits and low penetration. That is also the case on some of the jobs. Strength contrast at the face and uneven color wear, as well as clogging due to shale and clay seams. So clogging isn't necessarily a problem you would encounter in soft ground. It may affect you also in rock conditions. Large water inflows and grout washout, backfill grout washout, gassy conditions, as well as contaminated ground and groundwater. In soft ground, obviously, conditions or the risk profile, the typical geohazards are slightly different. Some of them are in common, but in this specific case, you would be dealing with phase instability, high water inflow, high water pressure, clogging, boulders, high permeability of materials, and loss of phase pressure, where you can't actually guarantee that pressure at the phase isn't lost. Low cover, blowout, air losses during hyperbaric interventions, as well as settlements, surface settlements, high abrasivity, poor directional control. Some of these soils are so soft that the TBM would struggle to keep line and grade. Buoyancy in some of the marine underwater tunnels, gassy conditions, and contaminated ground and groundwater, as well as in rock. Here is the typical risk analysis approach we utilize. It's based on the standard risk matrix setup, where the risk is a function of likelihood of occurrence and impact or severity. The ranges for impact on cost, time, health and safety are the ones that we typically adjust based on the project size, the value and duration. So what you see here as less than 10K or between 10K and 100K are the values specific to a project schedule and the project duration, as well as the time frames you see there. All those ranges will need to be adjusted based on the project. This one is a project in the $700 to $1 billion range. And of course, by defining specific risks and aligning likelihood and impact in terms of cost, time, and health and safety, we can then determine fully characterize the risk, then determine mitigation actions, including which will include the TBM type or specific TBM features, and determine a post-mitigation risk or residual risk towards the end of the table on the right side. When you translate that risk assessment matrix into what actually happens, what happens and where along the alignment, then you obtain, in our opinion, the best way to visualize what risks are happening where, or can be expected where, And here is an example of a risk profile for a tunnel in extremely variable ground, which is characterized by phase instability. A lot of those risks I listed a couple of slides ago, but specifically here, phase instability, large water inflows, surface settlements, clogging, not as extensive as on other jobs, but there is some of that in some of these sub-breaches. Toxic or explosive gas, boulders and cobbles, as well as blowout failure. Another example of what, two more examples actually, of projects where you can identify the effort we made to determine georisks translated into where they are and what their magnitude is along the alignment is provided here. These are alignments that have been divided in multiple sub-breaches in order for us to provide the contractor with a better understanding of the entity of the risk, which risk and how much in each one of those. The geotechnical hazards identified here are, again, a lot in common with the ones we've already listed before. I believe that something different for the second case down below is the buoyancy and the presence of obstructions, but everything else is pretty typical. So let's talk now about identification of other factors. As I mentioned at the very beginning, TBM selection isn't just about the geological and geotechnical condition. It ties also into other aspects of a life of a project. Other categories, what we call performance categories that are essential to be considered for TBM selections are obviously the tunnel purpose, the tunnel diameter, its length, and gradient. So all the geometry factors obviously have an impact. The type of lining does have an impact. Tunnels that are required to be with no lining or with no segmental lining obviously would definitely steer the selection of a TBM towards a main beam machine. But when segmentally lining is required, you might have a wider range of options based on the variety of TBMs available, as we said at the beginning. So the type of, then there are operational aspects like phase pressure within the machine capability. As you know, just to make an example, EPB machines do come with a technological limit in terms of phase pressure that is around 6 bar. It is very hard or difficult for an EPB machine to perform effectively or to even be designed to perform in pressure conditions above that limit. Flexibility to adapt to variable ground conditions, ability to advance in open and closed mode. This is the case in a lot of projects where hybrid machines are being considered and supplied. Ability to perform drilling for effective drainage or pre-excavation grouting. Excuse me. Ability to perform cut-thread maintenance safely and efficiently, as well as the ability to negotiate tight radius curves. And then there are considerations to be made on the MAC processing and handling, as well as on the size and location of the mining site. And something that many times is overlooked is the know-how availability, which we always factor into our recommendations, particularly at locations, remote locations where it's difficult to get the skill sets you need to actually run a complex machine like an hybrid machine would be. Well, that may become a determining factor, or at locations that are close by multiple tunnel projects where it's going to be difficult to staff the job, or where historically only EPB machines have been used, and you actually want, or you're leaning towards a slurry type of technology. Environmental factors are obviously MAC characteristics, amount and type of additives that are used for excavation and ground conditioning, wastewater production, treatment, and disposal. On some of the jobs we've been involved with, reutilization of the water has become a determining factor for the type of TBM technology being selected. Water consumption, power consumption, and availability, of course, and tunnel classification. Is this a tunnel non-gassy, potentially gassy, or gassy, just to use the terminology OSHA typically defines, and the terminology that is typically applied to tunnels in the USA. And then there is a whole section of the TBM selection process that deals with planning. Schedule and cost are key factors, where assembly and startup time or advance rate or the time it takes to reconfigure, if you're talking about a dual mode or an hybrid machine, the time that would take to reconfigure or convert that machine into a different mode of operation is definitely something you may want to consider, and its impact on the schedule. Cost is, of course, determining. The budget for a lot of these projects are extremely tight. The capital investment for some of these very sophisticated TBMs is high. Auxiliary equipment may be involved, are involved with any type of machine, but we know that some of these machines would require entire systems like a slurry treatment plant that comes with a cost. And of course, availability of used machines. Sometimes we are also asked to explore the market and determine if that specific diameter of a TBM and the specific type of a TBM can be found as used anywhere. And if that's the case, then that definitely becomes a factor in determining or deciding a machine instead of another. Health and safety is everywhere. Obviously, any of the bullets I've been covering so far kind of contain it. So that this is applicable to all the aspects, all the other factors we've been discussing so far. So let's get to the actually to the multi-criteria comparative analysis. So what's the output of all these efforts, right? The TBM selection used to be limited to dualism. It used to be open versus shielded TBM in a rock type of tunnel, or single shield versus double shield TBM, again, in a rock type of tunnel. In soft ground, for a long time, it's been EPB, air pressure balance, versus slurry TBM or mixed shield TBM. So this is a chart we can probably recognize and we are all familiar with, but that is what used to be. As I mentioned, with the development of hybrid machines, the typical EPB and slurry application fields have been extended. These two diagrams below now tend to overlap, and this helps mitigate a lot of the geohazards I've been discussing previously. Fields of application of different machine types are now overlapping, as I said. The same machine can support different excavation methods. We can call them in different ways. They are hybrid, they are dual mode, they are variable density, that is a specific type that does cover a very wide range. And they can mitigate georisks more or less effectively. We'll talk about the clogging potential a bit more later. The same machine can be set up in different ways. And here is a non-comprehensive list of typical things that are considered. Even after the TBM type is selected, there is a whole range of other toolbox items that can be implemented to satisfy specific project needs and to mitigate specific risks. Cutting tools, type, size and configuration, the 17 inches versus 19 inch, soft ground tools versus hard rock cutters, adjustable overcutter by shimming manually or by having an automatic system when access to the cutter is not that easy to get. stepped shields design, dual speed gearboxes for different heterogeneous ground conditions, standard low screw conveyor versus center screw conveyor, long screw conveyor versus short screw conveyor. We've seen that too being proposed by TBM manufacturers. It comes with pros and cons, as everything. Stone crusher at the excavation chamber or at the discharge point, having the ability to probe and grout. Biggest differentiator in this case is the operational performance field, due to the higher flexibility offered by a variable density type of approach. And here is the last part, which deals with quantitative comparison. So here is where we go into further discretization of magnitude and spatial extent of each risk factor, which has been already identified throughout this whole process. We achieve that by dividing the TBM tunnel alignment not only into reaches and sub-reaches, but into units of 50 to 100 meter length that are standardized intervals. And based on measuring the residual risk after implementation of different TBM types, we determine, we perform a post-mitigation assessment, and we determine the residual risk. This residual risk is illustrated per each standardized interval of 50, 100 meter, per each category, cost, schedule, and health and safety, and per each TBM type. So this gets to a level of complexity and to a level of detail that is definitely quantitative. In this way, we are able to determine the frequency of occurrence and anticipate the number of times each hazard will present itself along the alignment. And this whole process is actually performed in accordance with ITA guidelines for tunnel risk management that were released in 2004, again, for your reference. The same standard numerical analysis and color coding is used for these risk metrics. So I'm not going to repeat myself, but this is how the work is structured. And what you see here is the example of an alignment that has been divided in 50-meter intervals with the same top 16 residual risks ranked by each category. So each machine, this specific type of machine, EPB, is applied to the geohazards. Everything is scored in terms of residual risks on health and safety, schedule, and cost for the EPB alternative. And what you see in green is clearly the areas where the TBM, the EPB type performs at its best. Here is the same alignment, same project, with the risk determination and with the scoring performed at 50-meter intervals on the same risks for a slurry TBM alternative. And as you can see here, there is clearly an area where the alignment is marked as yellow, and that is where the slurry TBM doesn't necessarily perform as well as the EPB in this specific case, but more in general in terms of costs, due to the fact that there is the additional, you have to factor into a slurry TBM selection the additional cost that comes with the slurry treatment and separation plant. And this is the quantitative comparison, the output basically of this effort. So the numerical values are represented here on a typical risk matrix for each TBM type. And the size of the circles you see here represent the extent of the risk in numerical risks in numerical terms. In some of the cells you see 2 circles because this specific analysis was performed both on every 50 and every 100 meter zones along the alignment. But this is definitely a good picture in terms of cost, schedule, and health and safety of where the residual risk is by applying 2 different TBM technologies. And this is an example of the results as a bar chart, where you can see that the alternative one, the EPB, is showing lower bars in the range of relatively lower residual risk, negligible range of residual risk compared to the slurry TBM. Briefly on the conclusion, so we have a few minutes for questions. If the contract documents allow TBM choice, a multi-criteria analysis is, in our opinion, always recommended. The assessment process starts with independent and in-depth review of the GBR and GDR to characterize ground behaviors that are not necessarily covered in the GBR and define the main geohazards. The type of TBM and TBM features and then intended as mitigation factors, mitigation measures in the risk matrix, in the risk assessment process. As we've seen, geology is not always the only factor. There is plenty of other performance fields that will need to be considered. Incremental levels of detail of comparative analysis are possible, but this is based on the project complexity and the severity of the risks. So you can pick and choose a qualitative or a quantitative type of analysis based on the degree of complexity and how big is the challenge. A multi-criteria analysis provides technical validation of the most consequential decision, in our opinion, on any TBM tunneling project, which is the machine selection. With that, I think we can move into Q&A.
Yeah, absolutely. So thank you very much for that presentation. That was very informative. I'd like to direct everyone who has a question to the Q&A box. You're more than welcome to put a question into there. I have a few coming in already, so I'll filter and select here. Number one, so on the topic of lessons learned, this is a fantastic system, it seems, for numerical evaluation of TBM selection. Has your company or anyone in the industry done studies of after the project, analyzing the performance and seeing, is this model tracking that it's quite accurate in its ability to predict TBM performance, or are we seeing discrepancies between the assumptions made based on the GBR and then the actual performance or actual encountered conditions by the tunneling machine?
Yeah, great question. And this is the very reason we always like, as a company, to stay engaged, not only at the pre-design or design stage, but also during construction. We do need, in order for our methodology to improve, to factor into our methodology lessons learned. So far, yes, we've learned a lot, but in general, all the recommendations we've made through this methodology have then revealed themselves as very useful and appropriate during operation. There are obviously, specifically when it comes to not the TBM type, but more often to specific features, some of which I've already mentioned, to be implemented on the design or on the manufacture of the TBM. When it comes to specific features, then we've learned that the addition of more tools in the toolbox or specific tools in the toolbox would have been probably better. In some case, they were overlooked or not considered well enough in the selection process. It wouldn't have changed the final conclusion of that selection process, but those are the lessons learned and then we use the next time, right? So we are fine-tuning the qualitative and the quantitative assessment all the times based on what we learn in the field. And that is one of the main reasons, together with other things we do, we want to be involved during construction. Otherwise, we have no access to that information.
That sounds great. I think another question that's coming in here is it, I mean, I would assume this is very project specific, but in your opinion in general, is it better to have or assess the need for two different types of TBM in certain tunnel projects for different reaches where you can separate the reaches, hard rock versus soft ground, or is it more effective to employ the use of a more sophisticated TBM that can encounter all ground conditions with one machine? And I imagine there's quite a big cost to be quite a big factor in that decision.
Right. In this specific case, ideally, you would want to have the right machine for the right ground condition anywhere along the alignment, right? But most of the times, you don't have the access you need. You don't have a shaft right where, for instance, a shaft or an adit right where there is a boundary between one condition and the following one. And in most cases, the same TBM is called to mine the whole length of the tunnel through all the ground conditions. Also because the technology now allows that to happen from a point A to point B. But yes, ideally, if there are multiple accesses to the tunnel, or if there is a retrieval shaft big enough to be turned, retrieval site, to be turned into a mining site, you may want to have two machines mining opposite direction. That would make sense if ground conditions are extremely different, and if there is a clear definition of when one ground condition would turn into the next one. Otherwise, hybrid or dual mode or multi-mode is the way to go.
Okay, great. Really interesting question here is, in your opinion, is it better to invest when you're talking about, you have a budget for the project, is it better to invest more money in the initial geotechnical investigation to get more clear data, or to invest those assets into a more sophisticated TBM that you're more confident it can encounter any conditions regardless of what the GBR finds?
Unfortunately, it isn't a direct equation, right? It's not. It's not that. I mean, virtually, you would run no geotechnical investigation and put in the ground a multi-mode machine that is able to deal with. Well, it doesn't work that way. It's a lot more complex than that. So my answer to this is yes, definitely. Any effort that can be made and it can fit the schedule and the budget of a project at an early stage to collect the data needed to characterize the ground is definitely always money and time well spent, because that will also overall reduce the risk for the project and the cost for the project, right? Deploying a variable density or a multi-mode machine on a project that hasn't been well characterized isn't by itself a guarantee of success.
Okay, great. And then the last question, I think we're just out of time here. Has any MCA framework been used or created for TBM versus MTBM selection? So I imagine this is also, we talked about segmental, no segmental lining. How does this impacted by a pipe jacking sequence, for example?
So we've had a couple of opportunities to utilize the same approach, the same methodology also on micro tunnels. There isn't there obviously necessarily a variety of options as there is on larger diameter. But yes, this approach, this methodology has been already extended to MTBMs type of jobs. And it proven to be successfully also there. The experience we have weren't on the quantitative side. I believe they were both semi-quantitative, because that level of detail on the specific projects was enough to determine the best way to go.
Excellent, excellent. And with that, I'd like to wrap up the webinar. And first, I'd like to thank you, Martino, for your time. This has been a very interesting, I think I speak for everyone in the group here, that this has been an extremely interesting presentation, and Stefan Ferber for his previous talk that was linked to this one. I'd like to thank the UCA young members for helping facilitate this talk, helping market this talk, and we look forward to more cooperation between TAC and UCA young members in the future. For the TAC listeners out there, I'd like to remind everyone that the Tunneling Association of Canada Awards nominations are out and live on the website. So please check those out. We have categories like Photo of the Year, Young Tunneler of the Year, Lifetime Achievement Award, Project of the Year. If you think you're a good candidate for those awards, or you have a project which would be a good candidate, please apply. You're encouraged to. The deadline is end of February. Thank you all very much for your time, and have a great rest of your day and a great weekend.
Thank you.
Thank you all. Bye-bye. Until next time.